Welcome to this lesson on paper-based microfluidics. We're going to explore how simple paper devices can create sophisticated diagnostic tools without any pumps or external power sources. First, let's understand what paper-based microfluidics actually is. Microfluidics is the science of manipulating fluids at the sub-millimeter scale, typically in channels ranging from tens to hundreds of micrometers. Paper-based microfluidics uses porous materials, like cellulose paper, as the substrate. This creates channels and reservoirs within the paper matrix. The revolutionary aspect is that these devices require no external pumps. Fluid transport happens automatically through capillary action. Imagine the paper structure at the microscopic level. You have cellulose fibers creating a network of interconnected pores. These pores act as channels for fluid flow. Now let's dive deep into capillary action, the driving force behind these devices. What actually causes capillary action? This is a fundamental question we need to answer. Capillary action results from the competition between two forces, adhesion and cohesion. Adhesion is the attractive force between liquid molecules in the solid surface. Water molecules are attracted to the hydroxyl groups on cellulose fibers. Cohesion is the attractive force between liquid molecules themselves. This creates surface tension in the liquid. Here's a classic capillary tube. When adhesion to the walls is stronger than cohesion, the liquid climbs up the walls, creating a meniscus. The liquid rises until gravitational force balances the capillary force. Let's quantify this with the Young-Laplace equation. This is the fundamental equation governing capillary pressure. Delta P equals 2 gamma cosine theta divided by R. This equation tells us the pressure difference across a curved interface. Gamma is the surface tension of the liquid. For water at room temperature, this is about 0.072 newtons per meter. Theta is the contact angle between the liquid and solid. For water on cellulose, theta is typically around 0 degrees, meaning cosine theta is approximately 1. R is the effective radius of the pore or channel. Smaller pores generate higher capillary pressure. Let's do a quick back-of-envelope calculation. How high can water rise in a paper channel? Let's assume we have paper with an average pore radius of 10 micrometers. That's 10 times 10 to the negative 6 meters. The capillary rise height h equals 2 gamma cosine theta divided by rho gr. Rho is the density of water, 1,000 kilograms per cubic meter, and g is 9.8 meters per second squared. Plugging in the numbers, h equals 2 times 0.07, 2 times 1, divided by 1,000 times 9.8, times 10 to the negative 6. This gives us 0.144 divided by 0.098, which equals approximately 1.47 meters. Water can theoretically rise almost 1.5 meters in a 10 micrometer pore. In practice, due to irregular pore structures and evaporation, paper-based devices typically achieve flow distances of 5 to 10 centimeters, which is still remarkable. Now let's explore how we can engineer specific flow patterns by controlling channel geometry. You might be wondering, how do we actually create defined channels in paper? The most common method is wax printing. We print wax patterns onto paper and heat it. The wax melts and penetrates through the paper thickness, creating hydrophobic barriers. Here's a cross-section view. The dark blue regions are wax barriers that repel water. The white channel in the middle is hydrophilic and allows fluid to flow. The vertical lines represent the porous paper structure. For higher precision, photolithography can be used. This involves UV curable resins that create extremely well-defined hydrophobic regions. Inkjet printing of hydrophobic polymers is another method. This allows for rapid prototyping and low-cost fabrication. Let's talk about flow rate. How fast does fluid move through paper channels? The Washburn equation describes capillary-driven flow in porous media. L squared equals gamma RT cosine theta divided by 2 eta. L is the distance traveled, T is time, and eta is the dynamic viscosity. The key insight is that the distance traveled is proportional to the square root of time. This means flow slows down as fluid travels further. Let's calculate how long it takes for fluid to travel 5 centimeters in paper. Rearranging the Washburn equation, T equals 2 eta L squared divided by gamma r cosine theta. For water, the dynamic viscosity eta is about 0.001 Pascal seconds at room temperature. Plugging in, T equals 2 times 0.001 times 0.05 squared divided by 0.07, 2 times 10 times 10 to the negative 6 times 1. This gives us 0.000005 divided by 7.2 times 10 to the negative 7, which is approximately 6.9 seconds. So fluid reaches 5 centimeters in about 7 seconds. Now, how does channel width affect flow? This is a critical design parameter. Water channels contain more parallel pores, so they can transport more total volume per unit time. However, the linear velocity remains similar. Narrower channels are useful for flow focusing, creating concentration gradients, and enhancing mixing through chaotic advection. Here's a comparison. The wide channel on top and narrow channel on bottom have similar linear velocities, but the wide channel carries much more total volume. Surface treatments are crucial for controlling where fluid goes and how it interacts with reagents. Why do we need to modify the paper surface? The answer lies in controlling both fluid routing and biochemical interactions. Hydrophobic patterning, as we discussed, creates barriers that confine fluid to specific paths. This is the foundation of channel definition. We can create zones where capture antibodies or enzymes are immobilized. These zones catch specific target molecules from the sample. Reagents can be dried into the paper matrix. When sample fluid arrives, these reagents dissolve and react, enabling complex assays without user intervention. A typical diagnostic device has multiple zones. The sample zone receives the biological sample. It flows to a reaction zone where reagents mix. Finally, it reaches a detection zone where results are visualized. Let's look at a concrete example, a paper-based glucose test for diabetes monitoring. The patient applies a small blood drop, typically 5 to 10 microliters, to the sample inlet zone. As blood flows through the paper, red blood cells are physically filtered out by the small pore sizes. Only plasma continues flowing. The plasma reaches a zone where glucose oxidase enzyme is pre-dried. This enzyme specifically reacts with glucose. The reaction is glucose plus oxygen, catalyzed by the enzyme, produces gluconic acid and hydrogen peroxide. The hydrogen peroxide then reacts with a chromogenic indicator dye, producing a colored product. The intensity of color is proportional to glucose concentration. Results can be read visually by comparing to a color chart, or quantitatively using a smartphone camera and app. The entire process takes 1 to 2 minutes. Here's a simplified schematic. Blood enters from the left, flows through the paper channel, and reaches the detection zone on the right, where the color change indicates glucose level. Let's talk about cost, because this is where paper-based devices truly shine. A traditional polymer or glass microfluidic chip costs anywhere from $20 to $200 per device, primarily due to cleanroom fabrication. A paper-based device costs between 1 cent and 50 cents per device. This is a 100 to 1,000-fold cost reduction. Let's break down the cost of a paper device. Standard chromatography paper costs about 5 cents per square inch. A typical device uses about 2 square inches. Wax printing adds about 2 cents per device when done at scale using standard office printers. Reagents typically cost 10 to 30 cents per test, depending on the complexity. Enzymes and antibodies are the main cost drivers. Adding these up, 10 cents for paper plus 2 cents for patterning plus 20 cents for reagents gives us 32 cents per device. At large production volumes, costs can drop below 10 cents per test, making diagnostics accessible to low-resource settings worldwide. Now let's explore an advanced concept: three-dimensional paper devices. 3D paper devices consist of multiple paper layers stacked vertically. Fluid can flow both horizontally within layers and vertically between layers. Vertical flow occurs at points where holes in adjacent layers overlap. This allows for complex fluid routing in a compact footprint. Here's a 3D device schematic. 4 layers are stacked. Fluid enters the top layer, flows down through aligned holes to layer 2, then across to another vertical connection down to layer 3. 3D devices enable multiplexing testing for multiple analytes simultaneously. They also provide automated timing through varying flow path lengths. A practical example is a dual test for HIV and syphilis. Sample flows from one inlet and automatically splits to reach two separate detection zones in different layers. Let's address some key challenges in this field and their solutions. Challenge 1. Evaporation. Paper channels have large surface area to volume ratios, so water evaporates quickly in dry environments. Solution. Laminate the device with plastic tape to seal the top and bottom, or conduct tests in a humid environment. This extends working time from minutes to hours. Challenge 2. Quantitative accuracy. Paper structure is heterogeneous, causing variability in flow rates and reaction kinetics. Solution. Incorporate internal standard controls on the same device. By normalizing the signal from the test zone to a control zone, variability can be reduced significantly. Challenge 3. Reagent stability. Enzymes and antibodies can degrade when stored dried in paper, especially in hot climates. Solution. Add chemical stabilizers like trehalose, a sugar that protects proteins during drying. Package devices with desiccant packets and in foil pouches for extended shelf life. Let's discuss the real-world impact of paper-based diagnostics. A traditional lab test requires a trained technician, expensive equipment like spectrophotometers, consistent electricity, and sample cold chain transport. A paper device can be used at the point of care, in a clinic, pharmacy, or even at home by someone with minimal training. No electricity required. The malaria rapid diagnostic test is deployed worldwide. It detects parasite proteins in blood within 15 minutes, costs less than 50 cents, and requires no equipment. Over 245 million malaria tests are performed annually using paper-based devices in sub-Saharan Africa and Southeast Asia. This has dramatically improved diagnosis rates. Let's get technical about flow resistance, a critical design parameter. Flow resistance increases linearly with channel length. Longer channels mean slower flow and lower capillary pressure at the end. Resistance decreases as pore size increases and as the number of parallel pores increases. Wider channels have lower resistance. For a single cylindrical pore, resistance R equals 8 ETAL divided by pi r to the fourth power. Notice the fourth power dependence on radius. Doubling pore size reduces resistance by 16-fold. Question. If we have a long channel that's flowing too slowly, how can we speed it up? Answer 1. Increase the channel width. This adds more parallel pores, reducing total resistance without changing individual pore behavior. Answer 2. Switch to a more porous grade of paper with larger pores. Remember, resistance scales as R to the -4th, so this is very effective. Answer 3. Add periodic wicking pads along the channel. These act as intermediate reservoirs that refresh the capillary driving force. Now, let's explore multiplexing. How to test for multiple things simultaneously. Spatial multiplexing places different capture reagents in separate zones. Sample flows past each zone sequentially or in parallel paths. Here's a multiplex design. Sample from the center inlet flows down 3 separate channels to 3 detection zones. Each zone contains different reagents for detecting different analytes. Color multiplexing uses different colored dyes. For example, red for one protein, blue for another. A single zone can show multiple colors simultaneously. Temporal multiplexing uses different channel lengths, so analytes arrive at different times. This allows one detector to measure multiple things sequentially. How do we get quantitative results from paper devices? This is crucial for clinical applications. The simplest method is visual comparison. The device includes a printed color reference scale. The user matches the test zone color to the scale. This is subjective and operator dependent, typically providing only semi-quantitative ranges like low, medium, high. Method 2 uses a smartphone camera. An app captures an image, extracts RGB values from the test zone, and applies a calibration curve. Smartphone-based quantification typically achieves coefficient of variation of 5 to 15%, which is acceptable for many clinical decisions. Method 3 integrates printed electrodes. As reactions produce electroactive species, current or voltage changes can be measured quantitatively. Electrochemical detection is independent of ambient lighting and user color perception, providing more objective measurements. Let's look at an elegant design concept: origami paper devices. Origami devices are fabricated as a single flat sheet with fold lines indicated. The user folds the device, bringing different layers into contact. The folding action itself creates flow paths between layers and can induce mixing. This provides user-activated timing control. On the left is the flat device with a fold line marked in red. After folding, shown on the right, two sections come into contact, allowing fluid to flow between them. This is useful for multi-step assays where reaction timing matters. Each fold initiates a new reaction step with automatic timing based on flow distances. Let's look ahead at emerging innovations in paper microfluidics. Machine learning algorithms can now interpret complex test patterns, identifying disease states that humans might miss through subtle pattern recognition. CRISPR-based detection is being integrated into paper devices. These systems can detect specific DNA or RNA sequences with very high sensitivity. Wearable paper sensors attached to skin can continuously monitor biomarkers in sweat or interstitial fluid, opening new possibilities for health tracking. Researchers are developing dissolvable barriers that open at specific times, creating programmed sequences of fluid delivery without user intervention. Let's calculate the potential global impact of paper-based diagnostics. According to WHO, approximately 2.5 billion people worldwide lack access to basic diagnostic testing. If we compare a 50-cent paper device to a $20 traditional test, that's a 40-fold cost reduction. If 1 billion tests are performed annually, the savings would be 20 minus 0.50 times 1 billion tests. That's 19.5 times 10 to the 9th, or $19.5 billion per year in healthcare savings. Beyond cost savings, earlier diagnosis leads to better treatment outcomes and saves lives. The true impact is immeasurable. Let me summarize the key principles we've covered. Capillary action, driven by surface tension and contact angle, provides the pumping force. No batteries or external power needed. By engineering channel width, length, and connectivity, we control where fluid goes and when it arrives. Hydrophobic patterning confines flow, while immobilized reagents enable sophisticated biochemical assays in a simple paper substrate. The dramatic cost reduction, from dollars to cents per test, makes diagnostics accessible to billions of people who previously had no access. Ultimately, paper-based microfluidics democratizes diagnostic healthcare, bringing life-saving tests to the point of need, regardless of resource availability.